Here's our next section, which is 2.5. This brings in the second derivative. We've covered the first, done a little bit of work with that. And here's just a nice visual of three, the original function, the first, and the second derivative. We've got those three graphs there. And in this section, we're going to sort of figure out what the second derivative tells us about the graph and about the first derivative. So here is our first slide that gives us some notation. So you'll remember that we've got our Newton's notation. This is F double prime. That's the second derivative. And over here we've got Leibniz telling us that this is also expressed as the second derivative. Now, just because there's no fancy way of saying like that second derivative, but just to give you some insight, this is what that second derivative is telling us. It's saying take the derivative of this derivative function of y with respect to x. And so just some funky notation, because you have in the numerator these two d's, that's where we get the d that looks like d squared. It's not, but that's how the notation follows. And then here, because we've got the two dx's, it's read down here as the dx squared. So that's where that notation originates. Now what you have, it's a little cut off, but you can still read it. We covered this with the first derivative. You may remember, we know if our first derivative is positive, if f prime is positive, then f must be increasing. F has to be going up. And then we also said the second, if f prime is negative, then we know the original function must be decreasing. Well, we can use that same process and exploring what that says about the second derivative relative to the first. So if you look, boom, look, I just changed the first derivative. I put a derivative there, and then I put a derivative there. Then that must also be a true statement. If the first one was true, then these two must be true also. And this is telling us if my second derivative is positive over some given interval, I know my first derivative has to be increasing. If my second derivative is negative, that tells me that my first derivative has to be decreasing. Side note, folks, do not confuse positive and increasing. Positive is one thing, increasing is something else. Negative is one thing, decreasing is something else. You're just going to have to train your brain to distinguish between those. Meaning, for example, I could say, like at this stretch, let's call these A's and B's. Like from B to infinity, that blue graph, whatever it is positive and it's increasing. But from like negative infinity to A, I would look at that graph and say, those y values are positive, but that graph is decreasing. Why the heck do we even care? Well, it's because that second derivative information tells us information about the first derivative, and that first derivative is also going to tell us information about the graph of f. More specifically, the shape. So that last statement told us a positive second derivative implies that our first derivative is increasing. Now, let's look, because that is valuable information for what f is doing relative to the shape. If I am looking at these, I sketched this green graph, which is concave up, and there are some tangent lines on there. If we were looking at whether or not those slopes, what the trend is, we can see that they're super negative, becoming less negative, like it hits 0 here, a little bit positive, and even more positive. So as I'm reading the slopes of that graph from left to right, I can see that those slopes are increasing. So that first derivative being an increasing function now tells me what the shape of f must be. Those two are going to go hand in hand. If my f prime is increasing, bloop, it tells me what the shape of f is. Got to be concave up. So a positive second derivative implies f prime is increasing, and f prime increasing tells me the shape of f has to be concave up. So if we're going to play that same game with a graph that's now concave down, it's still the same idea, right? We would see now, what's that trend, folks? We're now seeing that my f prime is decreasing, and that tells me the shape of my graph. That's going to tell me that my f has to be concave down. So a negative second derivative tells me f prime has to be a decreasing function, which tells me that f has to be concave down. So let's talk about the converse. You might remember these from your conditional statements. The only thing that's different is that if I now refer to my function increasing, what that tells me is my first derivative is either positive or it could actually be 0. If my function is increasing, then f prime is either going to be greater than or equal to 0. I'll give you just a little quickie example right there. This is my graph of x cubed. And x cubed is a strictly increasing function. And the one thing that is kind of neat is that the derivative at 0 of x cubed is 0. The derivative is 0. I have a horizontal tangent right there. So even though my function is increasing, my first derivative is going to be greater than or equal to 0. First derivative is going to be positive or 0. And then the others also, so we're working with the converse, but then we're saying it could also be 0. Could also be 0. So if it's a decreasing function, then my first derivative is either negative or it's 0. And then the shape plays that same game. So if my graph is concave up, my second derivative is either positive or it could be 0. And then concave down, my second derivative is negative or it could be 0. So here's a question that is asked a lot. We are looking at shapes of graphs, and from there we want to deduce whether or not they would have a positive or 0 first or second derivative. So here is what I would like for you to do. So for example, for 1, which functions have a positive or 0 first derivative for all x? Immediately, since I'm given the graph of f, I'm trying to remind myself, like, what am I looking for relative to my f graph? So how else could I phrase that first question? We could phrase question 1 as, which functions are strictly increasing? Because if my function is increasing, my first derivative is going to be positive. So let's break this down and pause and see if you get the same answers. So for the first one, I'm looking for the graphs that are only going up. A dips, A decreases and then increases, right? Because right there it's decreasing, so no. And then we do the same. B is strictly decreasing. C decreasing. D dips down. E is our answer. So it's just E. And then we say the same concepts for the others. Which functions have a negative first derivative? So that's now asking, which of those functions are strictly decreasing? We already said A goes down and up. B, yes, B is strictly decreasing. So is C. D decreases and then increases. E we already said was, and then F. So B, C, and F would work for that. Now, 3 and 4, we are again phrasing so that it's clear what it is we're looking for relative to our F graph. So 3, I'm going to ask myself, or rephrase it to which function is strictly concave up, only concave up. A, clearly. Is B concave up? It sure is. B is concave up. C looks like it's concave down and then concave up. So we can't use that one. D is concave up. Is E? Oops. Yes. And F is no. And the last one, which one is negative? So now we're saying which ones are only concave down? Only concave down. No, no. This one is both concave up, F. And so that leaves us with F. If you're murky on concavity, here is something that I also like to think of is if my graph is concave up, and that what that means is if I were to ever sketch the tangent lines to any point, they would always fall below. Whereas if a graph is concave up, oh no, that was up, concave down, then all of the tangent lines would be above the graph. So if you were iffy on E, I sketch those tangent lines and I see that they're below, so E is going to be concave up. Sometimes you're asked to sketch the second derivative, not as frequently as graphing the first derivative. We can do this one of two ways, people. We could first start by just graphing F prime, if that green graph is F. And by doing that, this is going to be a good early chapter 2 review. We would find out where the zeros are, where those slopes are 0. And then here I can see that these slopes are positive, but they're becoming less positive. Oops, lost my 0. Positive, but becoming less positive. So my slopes would look like that. And then here, negative, more negative, and then right here, it switches gears and becomes less negative. Negative, more negative, switches gears, then like so. And then the last piece is positive, becoming more positive. So this would be the graph of F prime. The second thing I could do is give myself even more practice. I could sketch now the derivative of the red graph, because the derivative of red would be the second derivative. If I take the derivative of the derivative, it's the second derivative. So here, my red graph has its 0, and I can identify that these slopes here are negative but becoming less negative, and then positive and becoming more positive. So F double prime looks like so. What's even faster is we can see this part of my graph looks like it's concave down. So I know that my second derivative graph would look like this because concave down implies negative. And then here it changes and it's concave up. So here we've got a practical use for that second derivative. We will use this often where we are referring to S of t being our position function. We're introducing acceleration. That tells us the rate of change of velocity. So if I take the derivative of velocity, and you'll see that right here using our limit definition, the derivative of velocity tells us acceleration. It tells us then how fast are we speeding up, right? How fast are we slowing down? Because that is useful information to have. Now, down below, we're given, if we define S of t as position, we'll see both in Leibniz notation as well as using S double prime and V prime, how all of these things relate. So here is our Leibniz notation for acceleration. And then here it is using our position function, S double prime. And if I'm just referring to velocity, I know that acceleration would be V prime. So we have now talked about where your graph is concave up, where it's concave down, but now we're talking about this special point where your graph changes concavity. So here we have it. We know a point where our graph changes from concave up to down is referred to as an inflection point. So here is one thing that we know. A point where your second derivative is either undefined or equal to 0. So if f double prime at some point is equal to 0 or undefined, that is I'm going to circle this so hard, y'all, possible. It's a possible inflection point. So we do more to figure out if it is in fact an inflection point. So if we want to determine whether or not it is in fact an inflection point, we are going to need to see to the left and to the right of that point if our second derivative changes signs. Does it go from negative to positive if it's either equal to 0 or undefined? So let's see some application with this. Here is a question. This is an old free response question that asks, or here we're given that this graph is f prime. This is the derivative graph. And they're asking over what intervals from -3 to 4 is f both concave down and decreasing. So again, I'm going to think about this in terms of f prime. If they're asking me where is f concave down and decreasing relative to f prime, I want to figure out if my f is going to be concave down, then on this graph, I want to see, well, where is f prime decreasing, both decreasing, and if f is decreasing, my f prime is going to be negative. So I need to look at this graph and figure out over what interval is f prime decreasing and negative. So here is 1. We know that f prime is decreasing from the interval from -3 to -1. But remember folks, these are positive values and these are negative values. So I want decreasing and negative. So I know this stretch from -2 to -1, f prime is both decreasing, right? It's going down, and it's negative. It's below the x-axis. And then it's still negative from -1, but that's now increasing. And now this stretch, decreasing and negative. So I believe we found -2 to -1 is one interval. And I can just write and, I don't need the union, from 1 to 3. And it's telling me justify that. Give me a reason. Why is that so? And we could say that over the intervals from -2 to -1 and 1 to 3, because your derivative is decreasing and negative there. Now for the second part of this question, they're asking us to find all the inflection points of f. And remember, if I'm looking for the inflection points, that's where my f would change concavity. It would go from concave up to concave down or vice versa. What does that mean though, relative to my f prime graph? Remember, if my graph of f is concave down, I know f prime must be decreasing. If my graph of f is concave up, then my f prime must be increasing. So this question I can phrase and think of as, where is f prime changing from decreasing to increasing or vice versa? And let's see. Here, f prime decreases and then increases. So right at that valley, we have an inflection point. And then what happens? It goes from increasing to decreasing. So right here, I have another inflection point. So all of our, what looks like vertices of parabolas. All of these, so here we would say we have inflection points. F has inflection points. We would say that F has inflection points at -1, x equals 1, and 3, since F prime changes from increasing to decreasing or vice versa at these x values. This last piece is just on these specific questions where they ask, is the speed of this object increasing or decreasing? So, folks, speed of an object increases only when velocity and acceleration have the same sign. So that means if at some time t, both v and a are positive, then I know the speed has to be increasing. Also, when v and a are both negative, the speed of this object will be increasing. If they have the same sign, our speed is increasing.